Hello everyone, this is Dr. Lennon, and we are going to continue with exponential functions today. So just to review, an exponential function is one that takes the form y equals a times b to the x. So it has this form, y equals ab to the x. There's also an alternative form that we'll talk about when we get to the interest section that deals with different exponential the base written in a different way. So that's all I'll say for that right now. Again, the thing to remember here is a is the y-intercept, b is the exponential base, and it's related to the way that the output of the function changes. So typically this means that you're going to have a multiplicative pattern in the output variable, and that can be related to a percent change. So remember, the way to get the percentage change is we can write b equals 1 plus r, and then r would either be the percentage growth or decay if r is either positive or negative. So if you need a bit more review on that, I would suggest you go back to the previous exponential functions video and watch that over again. So let's pick up kind of where we left off. So in this first example, we are just going to find an exponential function that passes through 2 points. So we want to find the equation for the exponential function that passes through the 2 points, -1, 2.5, and 1, 4.9. So remember, what we basically want to do is plug both of these into the y equals ab to the x form. And I suggest that you plug the one with a larger x value in first. So if we do that, we'll end up with 4.9 equals ab to the first, and on the other side we'll have 2.5 equals ab to the -1. And then what we can do is we can combine those by taking ratios. So we would know 4.9 divided by 2.5 will be the same thing as ab to the first over ab to the -1. So in this way, the a's will cancel and we'll be left with one equation with only one variable. So if you put this into the calculator, you get 1.96, and this will be b to the 1 minus -1 from our exponent rules. So we have 1.96 is equal to b squared. Typically, your answer here would be plus or minus the square root of 1.96, but we know the exponential base has to be a positive value, so we can just say b is the square root of 1.96, which is actually exactly 1.4. So that's our value of b. So then to find the rest of the equation, we now know that our equation looks like y equals a times this 1.4 raised to the x. And we can plug in either of the 2 points and solve for a. So we would have 4.9 equals a times 1.4 to the first power, which is just 1.4. So we can divide by that quantity on both sides, and we get our answer, or our value for a, which is 3.5. So our exponential function here looks like y equals 3.5 times 1.4 to the x. And that is what they were looking for. So nothing too difficult there, and a good refresher. So now let's compare some sets of data from some tables. So example, when we look at these tables, we want to determine whether the data is linear, exponential, or neither. I forgot to write exponential. Or neither. So really what we're looking for is kind of a pattern in the output variable. So this first set of data will have 1, 2, 3, 5, and 12, 10, 8, and 4. So one thing to note is that your x values are increasing by 1 for the first two steps, 1 to 2, 2 to 3, but then it jumps from 3 to 5. So then what is the pattern in the output variable? Well, 12 to 10, 10 to 8, then 8 to 4. So it looks like it's decreasing by 2 for each unit time step. So that's why when we get the jump from 3 to 5, it decreases by 4, because it's going to decrease by 2 twice. So this is going to be linear. Anytime you see a constant additive change in the output variable for each unit time step, it's going to be linear. So here we can say the function is linear, and we know that change is actually the slope. So with a slope of -2. Okay, then let's look at another one. So this data set we have, let's say -3, -2, -1, 0, and 2. And our outputs are 288, 144, 72, 36, and 9. So what's going on here? Well, again, we see a pretty consistent behavior in the input variable. It's just increasing by 1 for each of the first 3 steps, and then goes from 0 to 2, so it jumps by 2 twice. Jumps by 2 in that last step. Then we have the outputs. So 288 to 144. Well, that's either subtracting 144 or dividing by 2. And then the next step, it goes down by 72. So the pattern clearly here is dividing by 2. And if you check going from 36 to 9, that would 36 divided by 2 is 18, and then divided again is 9. So we see the behavior in the output variable is multiplicative, and that's what's indicating that this is an exponential function. So we would say that if it's multiplicative in the output variable for each unit time step in the input variable, then it will be an exponential function. And the thing that you're multiplying or dividing by, that thing is actually the value of the exponential base. So the function here is exponential. With a base of 1/2. Okay, so our last one, you can probably guess what's going on here, or you might guess before I write down the data what's going to happen, but it's still worth analyzing. So we have 3, 4, 5, and 6. Okay, so what's going on here? Well, we have kind of that multiplicative behavior now reversed. So it's in the input variable. So we're multiplying x by 2 each step, but we are only adding 1 to the y value. So you still have multiplicative behavior somewhere, but it's in the wrong variable. So this is not indicative of an exponential function. The exponential function would have for each unit time step multiplicative behavior in the output variable. We'll see in future sections that this is actually going to be indicative of the inverse of an exponential function, which is the logarithm. But for this exercise, we say this is neither. So this is multiplicative in the input variable, and not the output variable. So let's go ahead and continue. We can now talk about, so we'll talk about first that exponential base I mentioned at the beginning. So you might ask yourself, here's just a question you might want to ponder. So what is the most important number we use as an exponential base? So this is not really, like technically something you would have to do, but it's interesting to think about. Like, would I pick 10? Would I pick 2? Would I pick some other number? So you can pause the video and think about that. But the answer is actually the special number we use. So it's on equal footing kind of with pi. So we have this other number, E, known as Euler's number. And I will tell you what that is if you have not heard of it before. So this is an irrational, actually transcendental number, 271828, and which means, one of the things it means is that it has a decimal expansion that goes on forever and ever and doesn't repeat in any meaningful way, and so it's a non-terminating, non-repeating decimal. So how does this number arise naturally in math is the other question you want to think about. So how does this number, where did it come from? Like, how do I get that decimal expansion? And it's actually pretty simple. So the answer here, again, is we look at a particular expression. So the expression is 1 plus 1 over n to the n. So think about this and think about putting different values in there. So if you put 1 in for n, this quantity would be 2, right? 1 plus 1 over 1 raised to the first power. If you put 2 in there, you'd have 1 plus a half raised to the second power, which is 1.5 squared, which is 2.25. It turns out if you allow this number n to get larger and larger and larger, this quantity will not blow up. It will approach exactly that number e that I just mentioned for the previous question. So as this is given larger values of n, the quantity gets nearer to e. So in the language of calculus, this is actually a limit. So in the future, you'll maybe come across those and you'll get used to this notation, but this is just saying if n could get really, really, really big, and you look at what that eventually gets asymptotically close to, it is this value e. And maybe the easiest way I could show you that is by maybe like a quick Excel computation. So what we can do is we can kind of plug in larger values. I'll just do it really quickly here. We don't need this. So let's say we have our value of n, and then we want to figure out what our expression 1 plus 1 over n to the nth power is. Well, we can put in a bunch of values. Let's say, I don't know, we did 1 and 2, so let's include those, but then maybe we can do 4, 8, 16, 32, 64, 128, 256, 512, something like that. And then what we can do is we can fill in this expression using an Excel formula. So you do equals, and basically instead of putting n, I just click the cell to the left. So I do 1 plus 1 divided by, and then instead of typing n, I'm going to select the cell A2 next to it, and then I'm also going to raise it to this cell value. So when I enter that, what I'm going to be able to do is fill this thing down. So you'll notice that these numbers are getting closer and closer and closer to that value that we talked about. We can even put in maybe a bigger one, something like, I don't know, 100,000. Eventually, the computation will be too exhaustive for the memory of the machine, and it might give an error, but it's still just approaching that value. So we see very quickly that as those values then get larger, we do in fact get closer to that number. So that's kind of interesting. Okay, so where does this come up? This comes up in the theory of compound interest. So there's kind of two forms of compound interest. We have interest compounded a specific number of times, and we have continuous compound interest, which is if you would take that limit and imagine compounding happening at every single moment. So this is a nice application of exponential functions that you see come up in finance. So let's talk about interest that is compounded n times annually. So in this, the formula here is A is equal to P times 1 plus R over N to the N times T power. So what do these letters mean? A is the future value or accumulated amount. P is the principal or present value, or the amount invested. You can think of it that way. R is your interest or earnings rate as a decimal. So for instance, if it were 5%, for R you would put 0.05. N is the number of times compounded per year. Annually. And T is the time invested in years. So that is your formula, and that's what each of the letters means. So the other formula we want to talk about is the formula that is compounded continuously. So that formula is actually much easier, involves fewer things. So we have A is equal to P times e to the RT, where E is that Euler's number that we've discussed. So let's just do an example where we plug in a few values with these. And if you take a class in business or go ahead and take calculus, you'll probably run into these formulas again. So let's go ahead and determine the value of, so let me write down the problem here. Just give myself a little more room. So example, let's determine the value of a $30,000 investment in an account with 3.2% interest for 5 years, and then I will tell you, we'll do it multiple ways, and each time I will change the compounding. So the first time we'll talk about compounded quarterly. So that's one thing that often occurs with these finite compound interest problems. They'll have code words that will tell you the value of n. So in all of these problems, we know that P is 30,000, R is 3.2%, or 0.032, which is what we'll have to put in, and T is 5. But n is going to change, and if it's continuous, then we use a completely different formula. So for this one, we have 30,000. So we're compounded quarterly, so that is telling me that n is 4. Quarterly is 4 times per year. So we have 1 plus this 0.032 over 4. And you want to watch out with parentheses as you're inputting this. especially in the exponent there. If you have to enter it, you want to make sure there's parentheses around the 4 times the 5 so that you're not raising it to the 4th power and then multiplying that result by 5. So what does that come out to? This comes out to, if I round to the nearest cent, 35,182.92. So the next one, we'll look at compounded monthly. What I will talk about, just before we do this, we're not going to do these computations, but code words that come up often when you talk about pay periods is you could either have semi-monthly or bi-weekly. That's often how people are paid. So semi-monthly would mean twice per month, and bi-weekly would mean every 2 weeks. A lot of times people will just assume they're the same or equivalent in their heads, but if you do the computation right, semi-monthly would be 24 total pay periods annually, whereas bi-weekly, well, there's 52 weeks in a year, so every 2 weeks there would be 26 pay periods. So there is a difference of 2 pay periods when you talk about them, so don't just use them interchangeably if you are confronted with a actual problem that requires specific details. So this one, that's all we have to do is use the same formula as above, but now we're changing both of those 4s to 12s. And as you might expect, we should get a slightly higher value just due to compounding more. If everything else remains the same and compounding goes up, you actually get paid more because you are earning interest on your interest. So that comes out, in fact, to $35,197.83, so about $15 more. But that increasing the size of the compounding periods, has a limit, and that limit is reached when you talk about compounding continuously. So all other things being the same in this problem, the most you could earn due to compounding alone is going to be given by the continuous case, and that formula is just A equals P times e to the RT, so we just have our 30,000 times e raised to the 0.032 times 5, and that comes out to 35,205.33, so about $8 more than we had from the monthly case. All right, so that's it for this video on exponential functions. This is Dr. London signing off.